Now, what we're looking at today and tomorrow, it's probably going to take us 2 days for this here, is addition and subtraction. Now, for the most part, when we add or subtract two things, if the denominators are the same, we add the numerators. Or if the denominators are the same, we subtract. So we either add them, the numerators together or subtract them from each other. So if we look at the first one here, 7 over 4x plus, let's see here, 3 over 4x, we're wanting to add these together, and the only way we can add them together is if the denominators are the same. Are they the same? Yes. So that means we can do what? 7 plus 3 over 4x, because the denominator does not change. 7 plus 3 would be over 4x, and that's our answer, yes? Well, 10 over 4 what? Flip it. 5 halves. Mm-hmm. Because there's a common factor of 2, we need to simplify it out. So again, just like with multiplication, when we had common factors on top and bottom, we had to simplify. Same thing here. If there's a common factor on top and bottom, we need to simplify it out. And with addition and subtraction, well, if we looked at the original two, 7 over 4x and 3 over 4x, there's not a common factor in either one. But when we added them together, we ended up getting a common factor. So this is it here. Now, x cannot be 0 because it would make the denominator equal to 0. Okay. Let's look at the next one. 2 over x plus 6 minus 5 over x plus 6. Can we add these together? Well, yes, because the denominators are the same. Well, correct. I was wrong there. We would be subtracting. So we'd be subtracting the numerators. Mm-hmm. So we'd be subtracting because the denominators are the same. So we'd have 2x minus 5. Well, that's it, because we don't have any common factors on top and bottom. And the 2x minus 5, there's nothing we can factor out. So that's as simplified as it gets. Eight over 12x minus 5 over 12x. Can we subtract these from each other? Mm-hmm. Because the denominators are the same. So the denominator would be 12x. Numerator we'd have 8 minus 5. Well, 8 minus 5 would be? Mm-hmm. 1 over 4. Because the 3 over 12 will simplify to 1/4. And we have 1 over 4x. And that's it. Let's look at the other, number 2. So we have 2 over 3x squared plus 1 over 3x squared. So can we add these together? Well, 2 plus 1 gives us over 3x squared. 1 over x squared. 1 over x squared. And again, we haven't mentioned the restrictions, but we still have those. We still have those values that where the denominator cannot be 0. So it works out on both of these here. X cannot be, well, 0 for either one because the variable's by itself. There's nothing being added or subtracted. Any questions on any of these here so far? So let's look at number 3. Can we subtract these here? So the denominator is going to stay the same. And the numerators, we're going to do what? 4x minus x, which is? 3. Mm-hmm. And for here, x cannot be what? Positive 2. Mm-hmm. Okay. How about the next one? Can we add these together? Okay, if I add these together, I would get
2x cubed plus 2 on top and x squared plus 1 on top.
Is there a greatest common factor on top? Well, yes. If there's a greatest common factor and we can factor it, we'll need to. So I'll factor it out. So what am I left with on top? Oh, wait a minute. Will these cancel?
Yep.
So what am I left with? I'm like,
What is the line equals 0?
no, it's the empty set. Now, if we look for zeros, x squared plus 1 equals 0. Well, we could subtract 1 from both sides, yes? Which will tell me x squared is equal to -1. Then we would square root both sides, because the square root and square would simplify. And because we square root both sides, we would have the plus and minus. And what's the square root of -1? It's imaginary. So this will never be 0, correct?
Negative have a square root of like I.
Any square root of a negative number? Yes. So this one here does not have any restrictions because x squared plus 1 cannot equal 0. Okay. So are we good with this here so far, yes? So when we add or subtract any rational expressions, we can add them or subtract them as long as what? The denominators are the, what if they're not? Well, we have to make them be the same. We have to make them be the same. We have to make them match. So so we see here, a over c plus b over d, well, we have to get the denominators to be the same so that we can add the numerators. The same goes for subtraction. Now, whenever we make the denominators be the same, we want to get the smallest possible number or expression for that. Because anything bigger will work, but we'll have to pull whatever common factors are back out. So to do this here, we need to find the least common multiple. Because the least common multiple is going to be the smallest number that both things would be the same. So before we look at this example, one thing we could talk about is 4 and 5. So what is the smallest number that I can make both 4 and 5 be the same? 20. So 20 here is the least common multiple. It's the smallest number that we can make both of these numbers be the same, both of them be alike. Is it the only number that we can have? Well, no. I mean, 40 also works. And we can have very multiple different versions of this number. But this common difference, this here, this extra multiple of 2 and 40 that 20 doesn't have, will have to come out of the top and bottom. So any additional factors that we put into the least common multiple, especially with addition and subtraction, will have to come back out later. So that's why we want this least common multiple. So when we look at this here, we want to find the least common multiple of 4x squared minus 16 and 6x squared minus 24x plus 24. Now, before we start searching and hunting for the least common multiple, we need to factor these. We need to factor both of these down as simplified as we can get them. Because once we get them as simplified as we can get them, we factor them all the way down, then it's going to be easier to see what the least common multiple is going to be. Now, if I look at 4x squared, what can we do? It is a difference of perfect squares, but there's also something else there. There is a greatest common factor of 4. I want to pull that out first. Because if we factor 4 out, I'm left with x squared minus 4. X squared minus 4 is still a difference of perfect squares, yes? So now, we can do the difference of perfect squares, which would leave us with what? X minus and? Okay. So this here is it all the way factored down. And this is the one we're going to look at when we start looking for least common multiple. Let's look at the other one, 6x squared minus 24x plus 24. There's a greatest common factor of 6 that we can pull out. And if we factor it out, 6 factored out of 6x squared will leave me with 4x plus 4. Because when we factor 6 out of 24x and 24, we're left with 4x and 4. Now, when we look at this here, because the 4 is positive, the signs are the same, and they match the sign of the middle term, and our middle term is negative. So both of these would be negative. Factors of x squared are x and what would our factors of 4 be? 2 and 2. And these work out to be the factors of these here. Now, when we talk about least common multiple, this is one of the ones that normally people get a little bit confused with greatest common factor. Because greatest common factor, we're looking for the smallest number that is in common in every term, one that is shared across all, the biggest number shared across all. Least common multiple, we're looking at both of these here and seeing what factors are shared, or which one has the most of each factor. Now, for this here, most of the sets of parentheses are actually going to work out pretty easily. I think they work out pretty easily. Now, we'll look at 4 and 6, then we'll look at the sets of parentheses. 4 and 6, we need to see what is the first number that I can make both of these into. So 24 is tempting. It is 12. Now, what we can look at is 4 is what? As its its products, the prime products, product of primes as simplified as we can get it, is 2 times 2. 6 is what? 2 times 3, yes? So when I look at this here, well, 4 has how many 2's? 2. So for my least common multiple, I'm going to have 2 show up twice. In red. I'm going to take these 2's. I'm not taking that one. Because since 4 has 2 of them, I take 2. Now the 6 has what? A 3, so I'm going to take that. So we have those. Don't know why I did that. As 2 times 2 is 4 times 3 is 12. Well, 6 times 2 is 12. 4 times 3 is 12. Now 24 does work, but once we finish, if we're actually adding or subtracting, when we get to the very end, with any other common factors that show up, kind of like the first few, we'll also have an additional common factor of 2, because of the fact that 24 and 12 will reduce by 2. We'd end up with a common factor of 2 on top and bottom. So that's why we're doing this here, because if I can reduce any common factors on top and bottom that we don't have to have, it's going to make it easier for us. Now, for the sets of parentheses, I think this is a little bit easier than numbers. Okay? So, I'm going to take everything here. X minus 2, x plus 2. I took both of those. Okay? Any questions on this so far? So we just grabbed both of these here. Now I'm going to look at the other one. So over here, So we already have, so it has x minus 2 and x minus 2, yes? Well, how many x minus 2's do I have already? 1, yes? How many does this one have? So how many do I need down here? 2 total, yes? So I need one more. Okay, we're done. So this one here, so minus and plus are different because x minus 2 and x plus 2 are two different factors. So we'll need the, like we did with the multiples, we need the most of each type. So over here I have 2x minus 2's. So I need 2x minus 2's. Well, over here I have 1x minus 2. Well, do I already have it down here? Yeah, because we have 2. X plus 2, okay, I still need this. I need to pull it down. So we need the most of each type. The only way I would add another is if one of these had 3 x minus 2's, then I would need 3 of them. Does that make sense? That's why I kind of like these here, because it's almost, well, no matter what happens, I'm going to take all from one of them. Because we ended up taking both x minus 2's, yes? Well, I didn't need this x minus 2 over here, because we have 2 over here. But hey, I don't have this one. Pull it down. That's why I think this here is a little bit easier with the sets of parentheses. Because when we look at numbers, we're having to break them down and figure out how do they work together. Well, with parentheses, hey, I need both of those, and I need one of those. We're just looking at the things, which ones are the same, that's what we want. Okay, now, we already said it, but really this is going to be 12 times.
So would you leave the 2x minus 2 plus the square? Or not square, but a square that?
We could have squared it, yes. Now, what the goal with this here is to find out what the least common multiple is. What is the smallest term that I can turn? Let's see here. A little much. I saw this here. What is the smallest term that I can turn this and this into the same thing? Because that's what our goal is. That's what the goal is for addition and subtraction. We want the denominators to be the same. So if the denominators were these two here, well, okay, the smallest thing I can turn it into would be this. Yes? So, what would I need to multiply 4 times x minus 2 times x plus 2 to get to this here? So I would need to multiply it by 3, because 4 times 3 would give me, okay, what else is this missing that this has? Because I would need to multiply the denominator, and well, we'd end up numerator as well to get these to be the same. Now, this isn't part of the actual, for the homework on these and the least common multiple, but I'm trying to tie this back in. Now, when we look at this one here, well, we have 6x minus 2 and x minus 2, yes? So what do I need to do to make it look like this? Because that's what it's missing that the least common multiple has, yes? Now, once we start getting into these a little bit more, and we start getting comfortable with this least common multiple, we won't always have to list it out. Because if I'm looking at these two as an actual setup, let's just say plus, and I'm looking at this here, well, okay, 4 and 6 are going to be a little bit challenging just looking at them. But if we could see, okay, 12, so this needs a 2, and this needs to be multiplied by a 3. Okay, that's a little bit challenging part, or the harder part. But looking at sets of parentheses, I need them to be what? The same. That's what we're going for, yes? Well, this has x minus 2, this has x minus 2. Well, this one has x minus 2 and x plus 2. We need them to be the same. Well, this needs a x plus 2. Because now it has x minus 2, and x plus 2. Over here we have x minus 2, x plus 2. Well, wait a minute. This one has an extra one. So we're going to have to multiply it by an x minus 2. That's where we're going at with this. So we look at least common multiple as a way to kind of see, okay, how is this going to work? And that's what our goal or aim is to get, is in the end, when we start adding, we'll have it so that the denominators are the same. This is kind of what the goal is. This is what we're aiming for. Now, the reason we don't want extra ones, well, is on the denominator, we won't have to multiply this out, kind of like with our multiplications. If it's the same on top and bottom, they'll cancel out, yes? But on top will be adding, so we'll have to distribute these, because when we get the denominators to be the same, we have to multiply them out. And you'll have seen already, because when we do higher powers, the more variables we get, the more powers we get, yes? So the least or the less of these that we add in here is the better, because here I'm just adding a first power polynomial, yes? Well, if I accidentally grabbed another x minus 2, it's not a first degree, we just added in a quadratic that we don't need. So it starts making these harder than they need to be. So we'll look at another greatest common factor, kind of looking at this here. And seeing how this works. Yes. Yes. Okay, when we look at this here, we have 6x squared minus 54, and 9x squared minus 54x plus 81. So we have a greatest common factor of 6 over here, because 6 will factor out of 6x squared, and 6 will factor out of 54, leaving us with 9. Now, x squared minus 9 is a difference of perfect squares, yes? Okay. I'll give you all a second here. I'm going a little fast. Oh, wait. Huh? So if we factor x squared minus 9, we'd get what? X minus. What can we do with the other one? There is a greatest common factor of 9, so we can factor it out of each term. 9 out of 9 would just give it, 9 out of 9x squared would give us x squared. If we factor 9 out of negative 54, we get negative 6x. And 9 factored out of 81 would give us 9. Since the 9 is positive, the signs are the same and they match the sign of the middle term. Factors of x would be x and x. Okay. And so far here, they're keeping these factors pretty simple and how they write out. X minus 3, x minus 3, x minus 3, x plus 3. So we can kind of see that pattern. Yes, it would be. Because if we look at the breakdown of 6, 2 times 3, and 9 is 3 and 3. So I would take both of the 3s. Let's do this in red. So I would take both of these 3 here because that's the one that they appear the most. And I would take a 2. So we have 2 times 3 times 3. So if I look at the sets of parentheses, I'm going to take both out of 1 because I'm going to need them all. Which one do we want to take both of? Out of the 9, so x minus 3 and x minus 3. Does it really matter which 2 I take? No, because I can just pick one of the polynomials and grab all the parentheses because we're going to need them. It just might be that the other one has more of one, I will have to add to it. So we'll take both of these here. Yeah, because we already have the x minus 3. We need the x plus 3. Because that's the only one we're missing. So for this here, 2 times 3 would give us 18 times x minus 3 times x minus 3 times x plus 3. So this here would be the least common multiple of these here, of these two here. Any questions on any of this here? Okay. Now I have more put in here, but I want to go on and move on to actually applying this. Bless you. Because I feel like we get the concept of what we're doing. Let's put some application or some why we're doing this into this problem. Now these two here, we can see the denominators are not the same. 9x squared is not the same as 3x squared plus 3x. Doesn't work. So just like what we did with least common multiples, we're going to need to factor the denominators if we can. Can we factor 9x squared? One term. 9x squared is as simplified as it can get. Well, I mean, we could write it as 3 times 3 times x times x. Yeah. Yeah, I mean, we could factor it down to a prime factorization, but I think we're good. Now, the other one, 3x squared plus 3x, yeah, we can factor 3x out of both terms, yes? So if I factor 3x out of 3x squared, well, the 3, we just get x. Because the 3 factors out completely, I'm removing 1x from x squared, so I'm left with x. Plus 1, because the 3x factors out completely, yes? Not factoring wise. I have a feeling, okay, y'all have a little more space than I do. I'm going to center this up so I have space on either side. Now, there's two ways we can go from here, because we need the denominators to be what? The same, yes? So at this point here, we can use least common multiple, and I can write out to the side of the paper, and looking at 9x and seeing, okay, what are the factors of 9x, and how do we factor this, and doing what we just did. But least common multiple, the reason we're doing that is to get in that mindset of we're trying to make these two be the same, yes? So, let me get a different color. I'm going to look at 9x squared and 3x times x plus 1. Well, one of them is 9x squared. We have a 9, yes? The other one we have a 3. What do I need to do to the 3 to make it be a 9? Times it by 3. Well, we have an x, right? This one has a x squared, yes? So is there any way I can turn x into x squared? I can times it by x, yes? So if I multiply 3x by 3x, I will get 9x squared, yes? So does this fraction here, the denominator, have everything that this one does? Well, yeah, so we're halfway to being the same, yes? So we need to ask it the other way around. So I'm going to move to the other side. So does this fraction have everything, so does this one have everything that this one does? Does 9x squared have everything that the other fraction has? It doesn't have the x plus 1. Because if it has the x plus 1, now they have everything. Now they match up completely, yes? Well, unfortunately, I can't multiply the denominators by something without multiplying the top. Because we can't just change the bottom, we also have to change the top. So, with this one here, x plus 1 on bottom, what would I have on top? Because what is x plus 1 divided by x plus 1? 1. So what are we really multiplying? By a fancy 1, yes? So it's not changing anything. Over here we have to do the same thing. So really that least common multiple, the reason we did that was to kind of get our heads around making the denominators be the same.
Would that just make the x?
So let's look at here on bottom. Well, on bottom we'll have 9x squared times x plus 1, yes? Plus, over here, well, 3x times 3x would be 9x squared times x plus 1. These need to be the same, because if they're not the same, we can't add or subtract. Now, if you notice in the denominators, I did not multiply through by the 9x squared. We don't do that. On all of these here, we're going to leave this as b. Because when we add them together, they're going to be on one fraction, yes? And when we had multiplication and division, if we had like parentheses on top and bottom, they would cancel, yes? So most likely, if I multiplied that through, well, then I would have to eventually factor it to see if there are like terms, yes? Now, what are we doing on top? We're going to be adding, yes? Because when we add fractions, the denominator doesn't change. So guess what we're going to have to do on top? We're going to have to multiply these out. So I'll write it out at first, 7 times x plus 1. And over here, we're going to have x times 3x. We have to multiply. We're going to have to multiply through for the numerators. Now, I probably didn't have to write x times 3x. We could have probably done that. Well, here we have to distribute the 7. So 7 times x will be plus x times 3x. 3x squared. Any questions on this here so far? Well, guess what we can do now? We can add them together. Now I'm going to put the 3x squared in front because it has the biggest power. Now the biggest question at this point is, will 3x squared plus 7x plus 7 factor? Right, because this one here we have some doubts, yes? So what was the one sure way we know if it factors? So our part of the quadratic formula, the square root of b squared minus 4ac, because we can plug it in here. We can plug it into a calculator. So that'd be the square root of, well, 7 squared would be 49 minus 4 times 3 is 12 times 7 is 4 carry the 1, 84. That's going to be a negative number. Whatever it is, it's going to be negative because 4 times 7 times 3 is going to be a lot bigger than 7 squared. So this does not factor. So that's as simplified as it's going to get. Now, I do want to talk about restrictions. The homework may or may not actually ask for them. But it's good to get in a habit of remembering these restrictions. That cannot be 0. So when we look at this here, well, 9 doesn't matter because we're not plugging any values in for 9. So the main ones we're looking at are x squared and x plus 1. What's going to make x squared 0? 0. Because it's just a variable, yes? Anytime we just have a variable to an exponent, nothing added or subtracted from it, it's going to be 0. How about x plus 1? -1. Because it's almost, we've gotten in the habit, we know that x plus 1 equals 0. We do the opposite. So we would subtract 1, and then we're done. So the main goal of this here is first get the denominators to be the same. Add or subtract, factor, find any like terms, cancel those out. So we look at this here. Well, we have 8 over 12x squared plus, here we have x over x squared plus x. Now it's very tempting, let's see here, I'm going to move this over just a little bit. There we go. It'd be very tempting to come over and say that this here is going to be multiplied by 12x squared. This one here is missing an x squared plus x. And we can solve this here. It's very tempting to be able to say this, but it's not quite right. Yes. So, stuff like that. Now, 12x squared, well, the 12x squared is as simplified as it gets. It doesn't get any smaller. Right. What about the 12 and 8? Mm-hmm. 2 over 3x squared. Sometimes this is helpful, sometimes it's not. And the reason I say that is because if, let's just say the other one had a greatest common factor of 4 we pulled out, well, the only greatest common factor between 3 and 4 is what? 12, so it'd be back where we were. Here, sometimes it's helpful to reduce on top and bottom for each one. Sometimes it's not. It's just depending on the case. Now let's look at the other one, x squared plus x. This has a greatest common factor of, and that would leave us with x plus over. Now here's what I was talking about. Is I can factor, we can see there's a greatest common factor of x on top and bottom, yes? So I wouldn't write this down. I'm going to show you because I could come here and say that these two simplify out. I'm just going to rewrite that whole fraction. Because they simplify out, leaving me with 1 over x plus 1, yes? Well, what does this other one have? It has x squared, yes? So wait a minute, am I just adding that x back that I just took away? Well, essentially, this one here, this is what I mean. So sometimes reducing them helps, sometimes it'll help, but then we've got to what? Put it back in. So if I left it, instead of multiplying the top and bottom by an x squared, I would have been multiplying it by an x. So we end up sometimes having to bring the factors back. Sometimes we don't, sometimes we do. It's just depending on the problem. Does that kind of make sense? So, since I told you to leave it as is with x and x, I'll put it back this way. Okay. So we have both of the denominators factored. We have them simplified, yes? So what does 3x squared have that this one doesn't? So it'd be 3x and 3x. We already have 1x. It's just not squared. So to make it squared, we'd multiply it by 3x. So now does it have everything that the other one does? So does the 3x squared have everything that the other one does? No. It just doesn't have the x plus 1. So really, the first main part is getting the denominators to be the same. Once we get them to be the same, then we're going to add on top and bottom. Now, a little bit more space. So, the denominators are going to be the same. Well, we'll have 3x squared times x plus 1. Over here, we're going to have 3x squared times x plus 1, because once I get them to be the same, I know that all of them are going to be the same. Now, on top here, we can go on and multiply through. You don't have to rewrite it. 2 times x is plus. So if you went on and rewrote it as 2 times the sets of parentheses, that's fine. There's nothing wrong with that. But for this here, we can go on and multiply it out. It's not too bad. Just 3x times x, or x times 3x would be 3x squared, yes? And now we're wanting to do what? We're wanting to add them together. So we get 3x squared plus 2x plus 2 over 3x squared times x plus 1. And I'll tell you that's as simplified as it gets. Because the only way that the middle term can really be bigger or smaller than the two sets of factors is if we're minusing something together. Now, they can be the same. If we have 1 and 4, then the middle term can be 4. It works out. But if the signs are the same, most likely the terms are going to be equal to or bigger. The middle term is going to be equal to or bigger than the factors of the first and third term. So this one here doesn't work. Because again, if we went to check it, we'd have 2 squared, which is 4 minus, well, 4 times 3 is 12 times 2 is 24, negative 20, does not factor. So this is it here. And our restrictions are, I'm just going to tell you, is going to be negative 1 and 0. Okay? And this is where we're going to stop for today.